Hey, differential equation students. What we have here is a spring word problem. And what we want to do is write down the differential equation that will describe the motion of the spring. A couple things to notice here. First off, notice that we've got pounds and inches. So you can notice already that we're dealing with an English system of measurement, not a metric one. You might also notice that we've got inches and feet, so we have to make a decision here on what we're going to be doing. We have to be consistent, so for this example, I'm going to use feet. Now just a reminder, what you're trying to do is write something of this form. Actually, later on, we'll replace the 0 with a function that'll talk about how we are forcing the spring. But for right now, we need the mass of the spring, gamma, which is the dampening constant, and K, which is the spring constant. So let me show you how we're going to find all this information. Just a reminder that in the English system, pounds refers to force. So the typical equation for the force due to gravity is F equals mg. In this case, we are given the force, that is the 12. We don't know the mass, but you know g, that's 32 feet per second squared. So solving that, we've got 12 divided by 32. We're dividing by 4 on the top and the bottom, 3/8. That's our mass. We've got another equation that when the weight is at rest on the spring, that mg minus KL equals 0. So this is going to help us find K. mg is the force due to gravity. We know what that is. That's the 12 pounds minus K times L is the length of the spring at equilibrium. In feet, that's 3/4. And it's pretty easy to solve that equation and see that K equals 16. Finally, we have this expression here that talks about the dampening, how much resistance the weight experiences at a given velocity. So this is force equals gamma times velocity. We know the force is 2 pounds. We don't know what gamma is, but the weight is moving at 4 feet per second, so we can solve for gamma. So with all that, we can write down the differential equation. Cool. We also have a couple of pieces of information here that are helpful for initial conditions. The weight is moved above the equilibrium point. Just as a reminder that when we do this, if this is the equilibrium point, we're going to count this direction as positive and that direction as negative. So when we say 6 inches above the equilibrium point, that is up here, we're going to say that u at 0 is going to be negative because we're above, and 1/2 because 6 inches is half a foot. U prime of 0, we're being pulled downward, that's going to be positive at 1 foot per second, so U prime of 0 is going to be equal to 1. Great, that is the initial value problem that corresponds to this spring problem.